All right, it's we're recording. Good. All right, so we're on example 6. It says write each of the following as the sine or the cosine of a single angle. So if you check it out here, we have the sum of two trig expressions, and they're in terms of sine and cosine, and we have two angles in degrees, 22 degrees and 13 degrees. So according to the instructions, it needs to end up being like sine of one angle or cosine of one angle. How are we going to do that? Any suggestions? Oh, we could turn it into radians, but that's not going to necessarily help us. How can we tell it's a sine? There you go. Yeah, you have two terms, and each of them have a sine and a cosine. And because sine is selfless, giving cosine a chance each time, this will end up being a sine identity. And now it's just a matter of what to do with the two angles. Do I add them or subtract them? I add them because sine times sine. Yeah, bless you. And if it's a plus there, it's going to be a plus here. So 22 degrees, 13 degrees. Yeah, so that turns into sine of, don't mess up now, 35 degrees. All right, cool. So in that one, we're not actually going to be evaluating it. 22 and 13 are not on the unit circle. 35, is that one that we could split up in two different ways maybe and find the exact value of? Is 35 degrees one of the ones that will work? Can we find unit circle angles that add up or subtract to give you 35? We can only do it if it's a multiple of what? 15. Is 35 a multiple of 15? No, it's super close though, but won't be able to get the exact answer. So that's not what we're testing here. We're just seeing if you recognize the identity on the right-hand side, and can you put it back in terms of the left side. All right, how's about this one? Sine, sine minus cosine, cosine. It's got to be a cosine because each term just has a single representative function. But the one that we memorized for cosine was cosine, cosine plus or minus sine, sine. And this one's sine, sine minus cosine, cosine. So what do we have to do first? We have to rearrange it. We have to get it so that the cosine's first. Now, of course, subtraction is not commutative. So if we write the cosine first, the negative has to stay there. Negative cosine x, cosine of 2x, plus sine of x, sine of 2x. So that's at least a little better. Got the cosine first, but there's still a problem. I still have a negative in the front, and none of the identities we memorized started with a negative. So guess what I get to do now? Factor it out. Good. If you factor it out, now you have cosine, cosine, and Zane, I'm sorry, I didn't hear you. What does this become? A negative. Yeah, good. And now on the inside, with the negative factored out, now I have cosine, cosine minus sine, sine. So I just got to carry that negative along that was on the outside. And now I know it's going to be a cosine of something, plus or minus something. So what is the sign in between the two angles going to be, plus or minus? Plus, good, because now we have a minus, and this one changes for cosine, so it's a plus. And now it's pretty obvious, right? You got x and 2x. And so we combine those and we get negative cosine of 3x. And that is the answer. So this makes a fantastic, what could be like a multiple choice question. And cosine of 3x could be an answer choice, as well as negative cosine of 3x. All right. So pretty easy there. If you spot two terms and you have sines and cosines or sines and cosines separately, as long as the angles are the same in each kind of pairing, it's going to be a double or a composite identity in reverse. All right, so we've learned sine and we've learned cosine. The other big trig function is tangent. So we do have composite identities for tangent. So here's the first one, and this one you already know, because tangent is what in terms of sine and cosine? Sine over cosine. So if you needed to find the tangent of a composite angle, you could use the two identities that we've already learned. You can write it as sine over cosine, and then use the sine and cosine identity in the numerator and denominator respectively. And that would be fine. You'd have everything in terms of sine and cosine. But tangent also has its own identity, and here it is. And you'll kind of like this one. Remember I said in the beginning that you might have an urge to just distribute the tangent, call it tangent of x plus or minus tangent of y, and in general that doesn't work. Well, for the tangent identity, look at the numerator. You can almost kind of pretend like it works. You literally just distribute tangent of x plus or minus tangent of y. The only thing is that's not the only thing you have to do. Then you have to divide by 1. And Tyler, what did this mean yesterday? Which means compared to what we started with, it's going to be the opposite sign. One opposite sign of their product. Okay? So distribute, and then all over 1, change the sign, the product of the two, tangent x, tangent y. You do have to memorize that one. All right? You think you got it? It's the pattern. It's easier to memorize. All right, so let's do this one here. Example 7. Find the simplified, rationalized, exact value of tangent of 5 pi 12 using both the identities above, and then verify in the calculator. Okay, so I'm going to start over here on the left. Tangent of 5 pi 12. Is 5 pi 12 on the unit circle? No. Does it simplify on its own to something on the unit circle? No. But if it were 6 pi 12, I'll call it pi halves and be done. So what we have to do is find two angles that add or subtract to give you 5 that have something in common with 12 other than 1, such as 6 pi 12s would be fine, but then pi 12 is not going to work because we can't simplify 1 pi 12. 2 and 3 would work, right? So 2 pi 12s plus 3 pi 12s. 2 plus 3 is 5, and 2 and 12 have a common factor of 2, 3 and 12 a common factor of 3. So now if we simplify that, we get tangent of 1 pi 6 plus 1 pi 4. You certainly can, absolutely. You could have done 8 minus 3, 8 pi 12 minus 3 pi 12. Entirely up to you. As I mentioned on Monday, as long as you're choosing angles that actually do, in fact, add or subtract to give you 5 in this case, and you use the identity correctly, you'll get the same answer each and every time. That's why they're called identities. All right, so here is where the fork is going to happen. From here, we're going to, let me copy that and bring it over here. We'll do that for part B. So for part A, we're going to go ahead and, well, let's use the sine over cosine identities. So if I write this in terms of sine and cosine, that's going to be sine of pi 6 plus pi 4 all over cosine of pi 6 plus pi 4. So that would be using the ratio identity, not having to really use anything new. And then, of course, I can expand the top and bottom using the sine and cosine identity. So it would be sine of the first, cosine of the second, sine, same sign, so it's plus sine of the second, cosine of the first. And then all of that would be over expanding the denominator, which is the cosine. This is the selfish one, so it's cosine, cosine. Cosine first, cosine second. Change the sign to a minus, and then sine of the first, sine of the second. And now we just have to simplify that from the unit circle. So there'll be quite a few ratios here. Luckily, they're all quadrant 1 ratios. That's nice. So they should all be positive. Sine of pi 6 is a half. Cosine of pi 4 square root of 2 halves. Plus sine of pi 4 square root of 2 halves. Cosine of pi 6 square root of 3 halves. And at the bottom, we get square root of 3 halves, square root of 2 halves, minus 1 half, square root of 2 halves. All right, so I'm going to come over here into this new column, running out of room. And let's see, in the numerator, I can probably go right to my final simplified answer. Square root of 2 plus the square root of 6. Square root of 2 plus the square root of 6 all over 4. And in the denominator, it's square root of 6 minus the square root of 2 all over 4. All right, so that is a complex fraction. So we can clean it up, right? State change flip or multiply by 4 over 4. Your 4's divide out. I'm going to write the numerator as the square root of 6 plus the square root of 2, and the bottom now is square root of 6 minus the square root of 2. So that just kind of lines up the terms. Those are conjugates of each other, top and bottom. Now that is a decent answer, but it's not the final answer. We want to rationalize the denominator. We want to rationalize the denominator because there is a simpler looking version of this. So how do we rationalize the denominator if we have a radical down there but we have two terms instead of just one? Well, what do we FOIL? We have to have something to FOIL it with. The conjugate. Yeah, there you go. So you're going to multiply by the conjugate of the denominator because that's what we're trying to rationalize. Now, in the denominator, when you FOIL it out, if you did it correctly, you should have no more radicals. You have square root of 6 times square root of 6, which is 6. And then on the inside, you're going to get minus square root of 12. Outside, you get plus square root of 12. That's why they're gone. They cancel. And then you're left with minus square root of 2 times square root of 2, which is 2. And in the top, you have the same thing multiplied together twice. So you could do square multiply double square if you want. Square root of 6 square root of 6. When you multiply them, you get the square root of 12. And when you double it, you get plus 2 square root of 12. And then when you square the last, you get 2. So don't forget the middle term in the top. All right, so now we can simplify. 6 plus 2, that gives us 8 plus, and the square root of 12 actually simplifies, doesn't it? It's not a perfect square, but it's 4 times 3. So the square root of 12 simplifies to 2 square root of 3. Yeah. And so the 2 square root of 3 times the 2 that's there makes that a 4 square root of 3. And all of that is over 6 minus 2, which is 4. And now we can do one more thing. We could split it up. We can either factor the 4 out of the top or put each term over 4. So 8 over 4 is 2, and then 4 square root of 3 over 4 is just square root of 3. So that last step is where some people get hasty and they make wasty. They'll divide out the 8 and 4, but then leave the 4 in terms of the radicals. So remember, you either put each over the entire denominator, or you factor out the 4 on the top and divide it out. Yeah. So 2 plus the square root of 3 is the final answer. It's the simplest looking version that is still exact. And it is an irrational number, so your calculator is not going to be able to convert that back for you. All right, let me load my calculator while we're doing this. So look at all the wonderful math involved with that. That's pretty good stuff. Feels good. Almost like good breakfast dessert. You don't usually have dessert for breakfast. You're not quite on breakfast yet over there, Marshall, right? You're still eating those eggs in the blanket. Okay. Now, when we do it the other way, we should get the same answer, right? When we use the tangent identity, if in fact they are equal. So let's try that over here. Using the same angles, simplified, we're just going to use the other version of the identity, which is a little bit easier to remember maybe, because remember you just distribute. So you get tangent of pi 6 plus tangent of pi 4. And at that point, it feels like you're getting away with something. Because you are, if you stop there. So now you divide it by 1, and what's the sign going to be here? If it's a plus here, it changes in the bottom, 1 minus. And then it's just the product of those two, tangent of pi 6 times tangent of pi 4. So I claim that that right there is also equal to 2 plus square root of 3. So let's evaluate this now from the unit circle. Tangent of pi 6 is square root of 3 over 3, right? Square root of 3 over 3. Plus tangent of pi 4 is 1. All over 1 minus tangent of pi 6 is square root of 3 over 3. Plus tangent of pi 4 is 1. So now we have a complex fraction. Can we say change flip here? No, because we have multiple terms. So here the quickest way to get rid of the complex fraction is just to multiply by 3 over 3. And if you distribute then, you're going to get the square root of 3 plus 3 all over 3 minus the square root of 3. Well, we just need to rationalize it now. And rationalizing it is going to involve multiplying by what? the conjugate of the side we want to rationalize. We want to rationalize the denominator, so its conjugate is 3 plus the square root of 3. We'll do one at the top, one at the bottom. Conjugate of the denominator. So now in the denominator, do that first, because that's where you can check your work. If you do it correctly, the radicals should go away. You're going to get a 3 times 3, which is a 9. And then you're going to get a plus 3 root 3, minus 3 root 3. Those are gone. So then you're left with minus square root of 3 times square root of 3 is 3. And in the top, the terms are commuted, but they're really the exact same thing, right? 3 plus the square root of 3, quantity squared. So again, you could do the square multiply double square. So I'll square the blue one. Square root of 3 squared is 3. If you multiply, you get 3 square root of 3, which when you double, you get 6 square root of 3, and then you square the 3 and you get 9. Is that looking anything like 2 plus the square root of 3? Maybe not yet. There's still some work to do. So again, combining the 3 and the 9, you get a 12 plus the 6 square root of 3 all over 6. And now we can divide out the 6 from the top, or put each term over the denominator. 12 over 6 is 2, plus 6 over 6 is 1, so we end up with 2 square root of, oops, I missed it there at the end, 2 square root of 3. And it does turn out to be the exact same. So if that was our ultimate goal, to get to 2 plus the square root of 3, which one of those was a little bit shorter? Yeah, the one in terms of tangent. It was one column. But which one was more fun? And the first. Yeah. It's like, what do you like better, Magic Kingdom or Epcot? I don't know. God, it's all Disney World, man. They're both good. All right. Fun. Okay. Example 8. Now we're getting into proofs. We have 3 new sets of identities at our disposal. All the other identities that we've already learned, they're still fair game. All the rules of algebra, still fair game. But now we have 3 new sets of identities in our arsenal. So we'll draw a line down the middle. Which side would you like to start on? The left, okay? There's a new thing to consider when you're figuring out which side to start on. Even though the right side looks like it possibly has more information, because it has quotients and it has 2 tangents instead of the 1, why the left? Yeah, your first priority on any proof or any equation, I caught a glimpse for the first time, okay, of the cool guy. Your primary goal is to get your angles the same. What's your goal number 1? Get your angles the same. All right, and so because the left side has a larger angle, it's a composite angle instead of a single angle, that's the side you want to start on. All right, and we do have an angle then, or an identity for the angle theta plus 5/4. But we have 2 of them. You want to use the tangent composite identity in terms of sine and cosine, or the one in terms of tangent? Why? Yeah, your target is the right side, and it's in terms of tangent. So let's go ahead and use the identity. This is the one where we pretend like we're getting away with something. We'll distribute, keeping the sign there, and then it's all over 1. Change sign, so now minus the product of those. Tangent of theta times tangent of 5/4. Sweet. And at this point, if you have a trig function of an actual angle, you can evaluate it. What is tangent of 5/4? 1. So we're left with tangent of theta plus 1 all over 1 minus tangent of theta times 1, which is just tangent of theta. And if you compare it to the right side, Tyler, are we done? You asked that question like on day 1. We're not quite done because the numerator has 2 terms that need to be commuted. So it has to be, but for the color change and the handwriting difference, they need to be exactly the same. The sequence of the terms and factors needs to be in the same order. What? From the identity. Right up here. It's okay. Goldfish memories run in the family. Yeah, no, it's from the identity. The denominator comes from the identity. Yeah, and then, of course, tangent of pi fourth is 1, so that goes away. So, carpe dime. Yeah, seize the money. Yeah. All right. No. All right, letter B. Letter B. Oh, I'll draw the line down the middle. Sweet. On which side should we start? The left. Why? There's two terms, yeah. So that's one criteria. But the overriding criteria is the fact that the angles on the left are composite angles and the angles on the right are single angles. So if you have more information in your angles, you want to start on that side. All right, so now the right side becomes my target, and notice they're all expressed in terms of single angles. So I have to expand both terms on the left using the composite identities. So you might want to start a little bit further to the left here, because each of those are going to generate two terms. So sine of x minus y is sine of x cosine y minus sine of y cosine of x. Know your identities. Plus, and this is pretty nice that this is a plus sign. If this were a minus sign, you would have to distribute the negative or put parentheses, because remember, you're about to generate two terms. But with the plus sign, you don't have to worry about failing to distribute anything. So now it's sine of the first, cosine of the second, sine same sign, plus sine of the second, cosine of the first. So again, if that had been a minus sign, both of these terms now would be negative. Yeah, it should be. Let me do that again. Sine of the first, cosine of the second, sine of the y, cosine of the first. Yep. Okay, so now make sure that you have different angles for each one. Sine of xy, cosine yx, sine xy, cosine yx. Yeah, good. Okay, so once you have it expanded out, now look to combine any like terms. Do we have any like terms? Yeah, we have a sine e cosine x and a sine e cosine x over there, and they're opposites. So two opposites add to give you 0, right? So those guys are gone. And then we have a sine x cosy plus a sine x cosy. One of them over there plus one of them over there makes two of them, two sine x cosies. And is that what we have on the right? Yeah. Yeah, now if we had two cozy sine of x, we'd have to flip it around to two sine x cozy. You don't want to get too cozy in here. Stay on your toes. Stay sharp. Be alert. These are easy if you know the identities, right? Yeah, they're not the hardest proofs by any means. Okay, example 9. Must be kind of ratcheting up a notch here. Prove the following identity. These are in terms of you, which hopefully you like you. You should. Should like who you are and all that good stuff. Positive self-concept. But if you don't like you, you can change you to X. On which side should we start? The right. Why? There's more terms, but the angles aren't the same. We have u's over here, and we have a 3u on the left. So even though there's only one term on the left, which one has the bigger angle? Sine of 3u. So with the new criteria, trying to get the angles the same, you actually want to start on the left, because it's easier to tear down an angle using composite identities than it is to build up an angle. So even though the right side looks more complicated, the left side is a denser nucleus. It has more info. So here's what we have to do. I have to somehow write 3u in terms of 1u. What could I call 3u? I could call it 1u plus 2u. Good. Why would I not want to call it like 100u minus 97u? That's just stupid, because it makes, that gets away from where we want to go. certainly 100 minus 97 is 3, but then we'd have like 100 U's and 97 U's. We're trying to make it smaller, so look at composing by adding. Very good. Now if I expand, I'll have sine of U, cosine of 2U, sine, same sign, and then sine of 2U, cosine of U. And if you compare it to the right, you're like, yeah, go me. I've got single U's now on the left, just like I need on the right. But what do I still have on the left? I have 2 U's. How can I get rid of my 2 U's and write them in terms of 1 U's? Yeah, I'm going to use the composite identity again. Okay? And here's where you have to be a little bit careful with your notation because parentheses are important. I'm going to call that sine of U times cosine of U plus U. For U plus U is 2U. Same thing here. Sine of 2U is going to be sine of U plus U times cosine of U. And now I can use the composite identities again. So parentheses are required here. So I have sine of U times, and again parentheses because we're about to generate 2 terms. So that sine of U is going to have to get distributed. So cosine of U plus U is cosine of the first, cosine of the second. Change the sign to minus, then sine of the first, sine of the second. Nice. And I need more room, so we can kind of remodel, scoot that over. And I'll do the same thing over here. Plus, that cosine of U at the back, you could leave it in the back if you'd like. But again, multiplication is commutative, so I'm going to go ahead and write it in the front here, and then put my parentheses. And now I'm going to expand sine of U plus U. So that's going to be sine of the first, cosine of the second, sine same sign, plus, and then sine of the second, cosine of the first. And in this case, the first and second ended up being the same. They were both U. Okay, now what? Now you probably want to peek on the right side. The right side, notice that everything is expanded, right? Everything is expanded, so that's probably what I'll do on this side eventually. Let's look inside the parentheses first. Make your Aunt Sally happy. I have sine of U times, what's cosine U times cosine U? Cosine squared of U, yeah. So that's how you write it, with the squared between the S and the U. Minus, what's sine U times sine U? Sine squared U. And then plus, on this one, cosine U, we're going to have sine U cosine U plus sine U cosine U. 2 sine U cosine U, yeah. Like terms. All right, now we go down to the next line. Cosine squared minus sine squared, is that Papa Pig? Not quite. Is it negative Papa Pig? No. If they were both positive, it'd be 1. If they were both negative, it'd be negative 1. But in this case, one's positive, one's negative, so that's no pid at all. So I guess we'll just look at the right side again. And again, we need everything expanded. So let's go ahead and expand it. Sine U times cosine squared is sine times cosine squared, exactly what I said. Minus sine U times sine squared U is sine cubed of U. Plus, we'll do the same thing on this side. Now, on the second term, there's nothing to distribute because there's only one term here. So we just multiply like factors together. So cosine times 2 times sine times cosine is going to be 2 sine U cosine squared of U. You only distribute if you have multiple terms. And now we look to combine any like terms. I have a sine U cosine squared plus a 2 sine U cosine squared. One of them in the front, 2 of them in the back, combines for a total of 3. So I have 3 sine U cosine squareds, and then minus the sine cubed of U. And from there, I wouldn't know what to do. So I look at the right side, and I'm like, I'm done. Oh, you'd hate to stop right there. There's one last thing we have to do, which is what? It looks like I need my cosine squared factor first. So I need to commute the factors in the first term. 3 cosine squared u sine of u minus sine cubed of u. And now they are the same. Yes.
We're going to test over problems that long.
This is not long. You haven't seen long. Yes, we'll test over this. No, not the grizzly bears. No. Dry koalas at the most. Maybe panda bears wielding bamboo sticks. But remember, you'll have a safety net. So like on the quiz we just took, it said on the directions, because I didn't get rid of it, 5 out of 6. The second section, you'll have a solving equations. And then the third section will be these kind of proofs involving the new identities. And you'll have like 4 out of 5. So there is a little bit of a safety net. If you can't do one, you should be able to do the others. So yes, and Anderson, how do you get good at doing these? Practice. There's no royal road to mastery. You just have to trudge through them. And they get shorter and shorter as you do more and more. Yeah. Hang on, my iPad's upside down. There we go. That was the last one. Yes. Yeah. I need to go ask Mrs. Lincoln, though, for sure. She's Precal boss. What test is tomorrow? Tomorrow is U.S. government. That involves a few juniors. How many will take an AP? Go. Okay. 2? 1? 1. We'll see. So the answer, yes, is we'll be doing problems of this length and level of funness.